Hello everyone, my name is Abhishek Sahu, and for my major exam presentation, I will be discussing a paper from ICLR 2025 titled LORA Pro Optimization Overview. This paper introduces a new enhanced method for parameter efficient fine-tuning that significantly improves the stability and performance of large language models. So let's begin by defining the core problem. We'll all know that foundation models are incredibly powerful. However, the training them from scratch or even full fine tuning them, what we call FFT, is extremely expensive. It's required massive amount of computation and memory to solve this. A family of method called PEFT or parameter efficient fine tuning was developed. The most popular of these is LoRa. LoRa is very efficient, but it has a well-known weakness. Its performance is almost always inferior to full fine tuning. This proper investigates why this performance gap exists and processes a new solution, LoRa Pro, to fix it. The solution presented in LoRa Pro at its core, LoRa Pro is an enhanced version of LoRa that focuses on stabilizing the training of the low rank matrices. The benefits are clear. It reduces memory and compute costs just like a standard LoRa, but it significantly improves the uh, convergence and stability of the LoRa matrices. It's designed as a uh, plug and play module, meaning it can be easily added to any transfer model, and most importantly, it's maintained or even improves accuracy, helping to close the performance gap we just discussed. Goal of LoRa Pro. LoRa Pro aims to make LoRa fine-tuning behave as closely as possible to full parameter fine-tuning without updating the full model. It does this by matching the LoRa's effective gradient to the full fine-tuning gradient, stabilize LoRa optimization, achieving full FT performance with LoRa parameters. The ultimate goal of LoRa Pro is make parameter efficient fine-tuning behave mathematically like full fine-tuning. Standard LoRa often fails to match the performance of full training because its low rank update point in the slightly wrong direction compared to the true gradient. LoRa Pro solved this by calculating the exact mathematical correction needed for the adapter gradients by minimizing the distance between the LoRa gradient and the true quadrant. It ensures the model learns as effective as if we were updating every single parameters, but with the friction of the cost. So now we go through the algorithms which are present in the papers. So first algorithm is LoRa Pro with SGT. Now let's look at the algorithm itself. The first version present in the paper is LoRa Pro using the SGD optimizer. This form the theoretical foundation of method. So let's start. First we'll initialize the variables. The algorithm begin with the initialization. We set up our time step t to 0 and slice our low rank matrices A and B. This sets the start pointing of for our optimization trajectory. Loop until convergence. Next, we enter the main training loop. We increment the time step and select a batch of data. Then we compute the standard LoRa gradients. Let's call them G LoRa using the standard backward pass. So solve Sylvester equation and update. This is a critical step to find the optimal update direction. We solve a specific linear algebra equation called Sylvester equation to find a correction matrix X. Using the X, we adjust the standard gradient into the optimal pro gradient according to the theorem 2.1 from the paper. We then update the matrices A and B using the correct gradients. LoRa Pro applies proper optimization to A and B instead of naive SGD output. Once the stopping criteria is met, usually when the laws converge, we return the final optimized parameter A and B. So now let's go to the algorithm 2, LoRa Pro with the Adam W. While SGD is great for theory. Modern large language model are using Adam W. So the paper provides a modified algorithm W2 specifically for the Adam W, which is what we use in practice. Step 1 and 2 in this slide. First, we are initializing similar to the SGD version. We start by initializing our matrices and momentum vectors in the loop. We perform forward and backward pass to get the standard LoRa gradient for A and B. In step 3, the low rank gradient correction. Here we apply the first correction. We essentially project the gradient to ensure they aligns better with the full rank matrix, full rank update direction, minimizing the approximation error. In step 4, equivalent gradient. This is a key innovation. Instead of applying the atom to A and B separately, we construct a virtual environment gradient. This represents the gradient of full wave matrix. Step 5, moments. We then update the atom moments, the momentum and variance. Using this virtual gradient, this ensures the optimization dynamics match full fine-tuning. Step 6 and 7, we solve the Sylvester and final gradients. Using the atom corrected equivalent gradient, we solve the Sylvester equation again to find the optimal projection back into low rank space. This gives us the final corrected gradient for A and B. In step 8 and 9, update and output. Finally, we apply the weight decay and the final update step to the matrices A and B. We repeat this loop until convergence and the output the final model. So does this actually work? The results are very impressive. This table shows LoRa Pro's performance compared to the best performing baseline like DORA and the Adalora on several major L benchmark. As you can see, the LoRa Pro consistently outperforms the previous state of art. It achieves a significant gain of 8.4% on the Alpaca Eval 2.0 and 3.9% gain on the math reasoning benchmark of GSM8K, and strong improvements across all other tasks. This clearly demonstrates its effectiveness. This brings us to the crucial question of efficiency. All these new calculations add a lot of overhead. The answer is no. Compared to the standard LoRa Pro adds only about 4 GB of GPU memory and about 10 minutes of extra training time. This still costs when you remember that full fine-tuning requires massive memory like 4 GB and more. The reason the cost is low and is that these new calculations like the orthogonalization are performed on the tiny matrix R by R matrices, for example, 8 into 8 and 16 by 16 matrix, not the massive million parameters model weight. So we get a significant boost in this performance and stability for costs that almost identical to start LoRa. So to the conclusion, this paper identified the key instability in standard LoRa, namely rank collapse and unstable update. Then proposed LoRa Pro, a solution that directly fixes these problems through three key innovation. One, progressive update schedule for the stability, orthogonal regularization to prevent rank collapse, and adaptive scaling to let each layer learn its own importance. The result is new state-of-art method for parameter efficient fine tuning that's stable, efficient, and highly performant, effectively closing the gap for full fine tuning. Thank you for all your attention. I'm happy to answer any question. Thank you very much.